Okay. I dropped my microphone, I can't hear. So anyway, I'm Bob Ciatti, lead for the systems group. I'm going to talk about Pleiades and some of the things that we're doing with the system and some things that we've observed in the last year. You know, so our average job size is around 2,000 cores, maybe a little bit bigger, maybe a little bit smaller. So at any one time on the system, it's likely that we're running 500 different jobs simultaneously. And so scientists and engineers would typically use this because they're solving fairly large problems, but they want several iterations over that problem in order to make some decisions about how they're going to proceed. And so it's based on an SGI system. And so the takeaway from this graph is that there's actually two of these hypercubes. It doesn't show up as well, but each of these points in this graph here is a vertex or an InfiniBand switch. And so this is actually an 11D hypercube. Each of the compute nodes on Pleiades is attached to both hypercubes. So there's IB0 and IB1. And so on some of the nodes, there's within each switch, there's 8 nodes that are connected, and some of the new systems are going to have 9 nodes connected to a switch. So it's a bristled, partial 11D hypercube. And we've modified OpenSM in order to connect up external switching to these hypercubes, because we're using dimension ordered routing, and that actually uses min-hop and then breaks the distance ties by using port order numbering. So the cables just got to be cabled regularly. And to avoid credit loops, since you're only using single DL, you need to have this weighting algorithm attach external switching. This external switching is in our I/O fabric, and all our Lustre file servers and the Hyperwall live off of the I/O fabric. And so this is just a look at what a file system looks like. There's 8 OSSs in MDS. There's actually 2 of these typically DDN SFA 10,000s these days that hang down off these channels. They're failing over by multipath. And each of the OSSs has their own dedicated switch, and there's a dedicated switch for the MDS. And so I've written a real-time monitoring piece of software that goes out and it actually queries this thing, and it's got about a 1 Hz sample rate. And so what you can see here is a no backup file system name, reads and write values, all the MDS and the OSSs and the totals down here. So and this might have been a peak throughput number. So what we see is that, well, on that NPB1, we hit a peak number of 16 gigabytes a second write bandwidth over that file system. And the time that I'd monitored this was probably going on for a couple hours. And so we bursted that amount of traffic into that group of OSSs. That doesn't mean it hit the disk, and the disk performed at that level. But the network that were connected to the OSSs actually had to perform at that level. So, out here on the end, so we said, well, we peaked out at about, coming into the fabric, about 16 gigabytes a second, and going out about 15 gigabytes a second. So that's what this I/O fabric bandwidth numbers are sort of get. We can see higher rates. Some of the file systems are underutilized or more lowly utilized than the other ones. So the InfiniBand specifics of Pleiades, it's got about 12,500 cables, or about 50 miles, combination of optical and copper cables. It's got about 2,900 switch chips. There's 2 subnets. Each of them have about 12,000 endpoints, because that's about how many nodes is in the system. 73,000 ports total, so it's about 1.5 million base counters. And so this is pretty close to what it was last year, but we have changed the system a little bit. So it's 11,700 nodes, or it will be. This is the April 12 target, and we're actually going to pull out 1,700 Harbortown nodes and replace those with Sandy regions. And so this is sort of the progression of the system over time. So in 2008, we had a first 64 racks. It was 393 teraflops. Added some racks. It went up to 565 to 92 racks. And that was actually our first top 5 result. It's grown to 112 racks, 144. So these highlights here on these are the hypercube dimension link connections. So what that's saying here is these are 8D connections across the rows, 9D connections across these 2 rows, and 10D across the 4 rows there. And so that's how the hypercube dimensioning routes actually on this topology. And so there's been several increases of the system. We've added some GPU racks, and so the final system there was about 1.33 petaflop total system in 2011. So what we're doing, you'll notice that we're removing this row of equipment here, and we're going to install some new systems. And so you can see up here, this is the cable infrastructure for Pleiades, and these are all the InfiniBand cables that go between those rows. And so we're lifting those cables up, and we're going to pull those 2 rows of racks out, and then replace them with some new equipment. And trying to do that while the system's in production, it's you know, so we're brave, if nothing. So there's some more pictures of the cables from the top and this infrastructure that we built with all these hangers to lift everything up, because the new racks, of course, are a little bit taller than the old racks, and so it's you know, a lot of things we do. And so just cables and cables and cables. Some more. And they don't always go where you think they went, because you know, we laid all this stuff in over some number of years, right? And so you get up on top and scratch your head a little bit. So anyway, there's the hole, and that's going to get filled in. So 1.7 petaflop total when we're done. OFED stack, we just recently deployed 1541. We're at the 3.3.13 SMs on both fabrics. The things that we're doing is, the interesting things we're going to be doing really in the near term is the suite management issues. And so I'll talk about this a little bit more, but we want to be able to down a port or a switch in the SM for maintenance. And so if we want to swap out a switch or we want to swap out a cable, we want to be able to go into the console or configure a file and say, okay, reread this file, and we'll disable, we'll route around actually a switch or a port before we disconnect it. And so that has some advantages, because that'll reduce the packet loss that we see when these traps get back to the subnet manager and you rescan. So what we've noticed is things are very disruptive when pieces of the fabric goes away, but if you're adding fabrics, if you're adding switches, that usually typically works because you're creating new routes. The old routes were good until you lay down the new ones, and so we're going to kind of do the reverse. So we're going to sweep and scan program with our, the topology that we want, and we can remove connections or switches, and that should solve some problems. The other one is that we want to scan and program only the switches that have routes, and maybe we use the cached values from the old, the last good known value for all the nodes in the first sweep, and then we go out and light sweep. So what this will do is it will reduce the number of input when we're programming the fabric, and so you want that to go quickly. And so that can take a long time because you time out a lot of these subnet packets that are going to nodes that are down, or just parts of the system may have a problem. So we deployed QoS, and IB0 allocates 3 VLs. About a half goes to MPI, a quarter to IP over IB, and a quarter to the BAT server. So the BAT server is just, it's running PBS, and so it goes out and talks to all the nodes, and so I just allocated a VL to it for good measure. It might not have been necessary. IB1 allocates actually 8 VLs, and so, and these are done through the SL mechanism. So we do the SL to VL mapping, it's 1-to-1. And so we're allocating 75% on IB1, which is our primary fabric that does I/O, 50% MPI, a quarter IP over IB, and a quarter to the Lustre MDS is all in that 75% high priority VL, and then 25%, which is one per Lustre file system complex. And so this is similar to sort of what Livermore had done with Lustre, which was to give 90% to the MPI and 10% to Lustre, just to ensure that Lustre traffic got through. And so, because Lustre can have problems if you block it. So in the build out of Pleiades, what we found is that packet loss is problematic. And this has been our experiments over the last few years. And so jobs would fail, and clients would not be evicted if we were growing the system. If we were shrinking it, it was the other way, though. We'd experience MPI job failures, connections between jobs would fail, or we'd get clients evicted, and so Lustre would fall over. And so in Lustre, actually, it would fail, not always in a transparent way. And so that's what we actually asked for, was a modification to tell us what pages you lost when you're evicting a client, because the client should know. And so when you have the state difference, we wanted to know which files were actually changed, so this actually changed some logging software. So what can happen is when Lustre goes bad, so Lustre server says, okay, I'm evicting logs. And it's trying to communicate with the client, and it decides, okay, well, I can't talk to that client. So it's because a reliable QP is associated with that connection. So if that reliable QP happens to go down, that type of log revocation is not a resendable message type in Lustre. So if that QP drops, the server considers the client down and evicts him, even if he's got dirty pages. And so when a client gets evicted, though, it's not always the case that the application running on the client knows about it, because that application may have exited already. And so it's a problem that, so the Lustre, we're going to submit up some cases on this, but there's still this issue, in an MPI as well, that you have, connections that if you drop a QP, it's difficult to maintain enough state for every message, and there may be a lot of overhead associated with it. So there's some messages that are critical. So if you happen to lose these critical packets, whether it's an MPI or Lustre, it bubbles up to the application. And so that's a problem. And so what we've done to correct this mostly is we bumped our subnet timeouts now up to 20. And so that's a big number. So our packet subnet timeout is 4.29 seconds per packet. And so, and then the connection manager will actually double that to 8 seconds per packet. And then he might try that, up to 7 times, right? So that tells you about the, we get a minute or so worth of instability in the fabric that we can cover with that number. But this is still really an issue at the ULP. How are we going to better ride through fabric instability? So these are performance counters that we've pulled, and so I've got them for IB0 and IB1. So what we've got here is we're just showing transmit discards primarily as they relate to link recovers and link downs. And so the link downs are the number of link downs per day. Here's the x-axis, so 10 link downs. And so the colors here are a little bit hard to see. Link down is the darker one, so that's the lower lines here. So, every day on Pleiades for the last 49 days, we're seeing, order 10 link downs, sometimes 100 link downs. The number of link recovers that we'd see are, averaging about double that, or, 5 times that, maybe 100, 200 link recovers on some days. But transmit discards are much higher, so the transmit discard numbers are getting into the 10,000, 100,000 kind of packet number for the day. So if any of these packets that you're throwing away are critical to an application, it can bubble up and cause problems in the application space. And so, yeah.
Your link down from what?
Well, so a link decides it's not going to work anymore, so it just goes down. So it loses link layer. What's that?
Is it a bad cable or ultimately diagnosis?
Well, so yeah, I mean, so we're pretty aggressive on swapping out hardware and cables and things, and so there's this is 12,000 cables in the system, and so this is the best that we can do. And so some of these things might be temperature related. So one part of the computer gets hot and cold depending on what kind of applications you're running, and so, or the cable could go bad. So maybe an analyst, hardware engineer, was working in a cabinet, changing out some equipment or some nodes, and broke a cable. Maybe I don't know, a whole set of different things. Maybe it's just gone bad for some reason. So we try to get them out as soon as we can, but replacing cables is also problematic because that can cause issues at the application layer. So these are just actual numbers, and they vary between fabrics. So this is IB1, and so you can see that the link recovery rates are actually higher a little bit, as well as the peaks for the discard rates on IB1. But IB1 is typically less utilized because MPI defaults to use a single plane on IB0, and as a result, MPI generates the most traffic as far as traffic on the system. But I/O is done on IB1, and so I/O is a little bit different because you've got these longer fat pipes of data that are sort of snaking down from the I/O system into the nodes. And so if you've got this big slug of data coming through and you drop a link, or you go into recovery state on a link, you start throwing stuff away, and you might rescan, and so you end up throwing away a lot more packets. And so I don't understand the mechanism yet, but we're getting a handle on it. And so VL15 drops are sort of at the sort of steady state across the day.
Can you make any comments on how does that correlate to application interrupts?
I'll do that. So okay, we'll get to that. And so so this is symbol errors and receive errors. What we see on IB0 and IB1 is a little bit different behavior. So for some reason on IB1 we see a lot more error rates, symbol errors and receive errors. And so I mean the receive errors are the ones that you care about, right? Because those are packet drops. But so we're seeing an order of magnitude at least increase in the number of receive errors on that fabric. And so this is sort of a natural variation. Everybody's going to have different error rates. So this sort of gives you at least a bracket where to go, that we're not, this is an upper threshold. So we're seeing tens of thousands of receive errors a day on the fabric, on one of the fabrics. And so let's compare, transmit discards to receive errors. So in IB0, so this is also the source of packet loss, right? So, yeah.
Do you attribute it to age of equipment type or what, anything like that? Or?
It's the best job you can do on a big InfiniBand network. So I think, we work really hard at it. We maintain it pretty well. And you replace cables. Sometimes they just need to be reseated. And,
because of your scale
yeah.
and several generations of equipment, I think you'd be uniquely qualified to talk about which things, some comparisons between some of these reasons for faults of and also the reliability of the different generations.
And interoperability as well.
Right. So,
Or lack.
I mean, each of those questions I can probably specifically address. And so, one issues that we've seen is you'll get a batch of cables, 1,000, and 500 of them will have, will be below margin, and they'll show error rates higher than the rest of the batch. So you sort of weed those down, and you might replace 200 that have the worst problems, but you still have 200 that are in there that are flaky occasionally. And so you're going to go, and it's pretty disruptive and time consuming to replace 200 cables. And so over time, this you know, we get new batches of cables and you try to weed them out, and there may be temperature variations. So why do some links sporadically fail? And so I think there's some more analysis. We're collecting all this data. We can go back through it and I think try to draw more conclusions than we have. Okay, well, what is the nature of this? But you know, I think at the base level is that this is the reality: is we're going to have packet loss on InfiniBand for reliable connections, and we got to deal with it. So, Jeff, yeah.
So how often have we? I haven't kept track. How often have we actually gone as far as replacing switches? Because that does that every once in a while.
Switch failure is pretty infrequent, but you know, so maybe every.
Right. So it's primarily cables. HCAs and switches are still pretty reliable.
Right. Mm-hmm. These are only switch-to-switch connections. So this does not actually deal at all with the switch to HCA connection. And so in this ICE system, it's actually through a backplane connector. And so those connections are much more reliable than the cables. And so we typically don't see problems there. And if we do see a problem, it's typically a problem in the HCA, although sometimes we'll have interface or mechanical issues on those connectors that'll cause problems. But I just wanted to isolate that part out. And so, yeah, yes?
So do you, when you mentioned that 50% of the cables are low margin inspection, do you go through any process to burn them in at all, try them before you deploy them into the data center?
Well, so we're sort of relying on the data chain, you know, the supply chain to do that, right? So because they're getting thousands and thousands of cables. So once they get to on-site, what we're expecting is that the OEMs or the vendors of the cable manufacturers would have done the work. And so they're, you know, so mostly some 25,000 cables. So if we had a batch of 500 that was wrong, then we get it right most of the time. And so it's the issue that we had most of the problems with were these hybrid cables. So they were going from a DDR to a QDR, so they had QSFP and CX4, you know, and that particular combination was bad or worse than others. We also found, though, that, and I'll show you in a little bit, that generationally things are getting worse, not better. So, yeah.
You actually lifted the cables?
Yeah, we did.
And
So,
did you see a rise in the jump in failures?
well, so somebody turned off my, you know, error monitoring stuff in cron during the dedicated time, and I just discovered that it was off last night. So I turned it back on, and we'll see what. And I've got another redundant database somewhere that I can pull that from. So we'll see. But you know, when you move a cable, sometimes you get some symbol errors. It typically doesn't make the link go down unless you have a problem. And so they broke some cables when they lifted it up because you know you can't see everything that you're doing.
So another question, so you're monitoring both simple errors and going down and up. Do you also monitor if they come up with the wrong speed? Let's say it comes up at SDR, do you have some sense of DDR should be DDR?
Yeah. And so you go out and you scan for that, and we find those, and either we might let it run at that speed if it's not. We have an issue specific to the architecture that we're only using a single VL to route. And so because of that, there are certain permutations of topology. If you pull a cable, you might get a credit loop. And so in general, it's not taking the whole system down. But there are some paths that are more heavily used than others. And so if those, and we've modified actually, I think it's IBCV or IBDM check actually to print out the entire loop that's involved in a credit loop, and then so we use that as part of the analysis to determine, you know, what the maintenance action is going to be. And so it's, you know, on these cables, that's another issue is that we, you know, typically have to, smart guys got to get involved in figuring out, okay, what are we going to do with this cable? So it takes a lot of time to figure out, okay, we're going to pull this one, we're going to you know, replace it, or we're not, we're going to wait, we're going to do that, so that just slows down things. Yeah.
Considering you're doing a cable lift now, the future racks you're putting in, are there new cables going to be already in the second trough now, so that they don't have to be, and if you're going to do another lift, but
Well, they're going to be sort of that height for a while, so I don't think we'll worry too much about it. And so we'll probably decimate some more of the Harbortown racks, and so we'll just kind of bubble it through. But I mean, this is operationally, you know, the reality is you need to move some things around. Typically, we want to keep the system up 24/7. Our experience here is really good because you remember the old days when you had big wads of copper cables going down. You couldn't move a machine, you know, so when everything's optical and you have so much space and we can cable over the top, it does give us a lot of flexibility in expanding things and moving things around. So I think that's been actually very successful because it allows us to meet, you know, these operational requirements, keeping the system going 24/7.
I mean, I almost would think now that you're going to start doing a few different bundles so that if you do a lift this row, you will know you only have to touch this level.
Well, you know, so it's not, well, so that infrastructure that we use to raise the cables, we're going to remove that when we're done. So they'll just go back and lay down. So, you know, when we're installing new equipment, though, you know, Matt and the hardware team will have a little bit more, you know, forethought. Okay, well, maybe, you know, when I took that apart, you know, it was because we interleaved all these things. And so, you know, we'd probably do a better job of reducing, you know, the map, right? So the number of tangles that you might have, and so you won't eliminate them, but I think you'll probably get a little bit better. But it's sort of unusual because we're 4 years into the production of the system now, so yeah, we're getting close. Okay, so let me go on here. So transmit discards versus receive errors on the two fabrics, and so IB0 and IB1. So you can see typically discards exceed receive error rates. And so that means that we're throwing away packets by, you know, whatever means, right? So we decided to throw away the packet. That problem is worse than the physical layer corruption of packets, right? That you get receive errors. And so we've got two sources, and the worst one is discards, throwing them away. So here's a distribution of error rates by location. So this is the rack number on the system. So it goes from rack 1 up here to 224, and these are 8 rack groups. So 8 racks makes up a 5D, 6D section of the hypercube. And so these are all 6D sections of the hypercube. And so this would be our DDR-based switches, and these were our QDR-based switches. So you can see that QDR has actually gotten a lot better at throwing away packets. It's, it's much faster. And so, well, you'd probably expect that because you're injecting more packets, right? So it's, you know, so proportionally it's probably doing better. But the point here is that the distribution in space is that you see these discards are everywhere in the system. They're spread out over lots and lots of switches, where the receive errors are these, you know, little impulses, and so they're fairly localized. And so what that means to me is that discards are in fact more insidious because they're unhealthy hardware. They're happening more often than receive errors. And so as a result of this, we really need to deal with it. And so this is the same chart again for IB1, and so it shows up a little bit nicer on this one that, yes, discards are everywhere on the fabric, and we see these little impulses of receive errors on, you know, things that were bad cables. So this is error rate by location, so these are link downs, link recovers. So this is what you see is typically these recovers and downs are associated with links, and they're actually associated with you know, symbol errors and receive errors, although I want to do the statistical analysis on it to be sure. And so in other words, you typically don't see sporadic, just a link going down. You get some indication. It may flap a couple times and then it'll go down. Then we have IB1 as well on this. So it's the same sort of thing where, you know, by location we still have these physical layer problems coming up, but they actually can translate into big swaths of discards happening. So you have a link goes down, you reroute the fabric, you're going to throw away a lot of packets because you've got problems out there. And so that means that a physical layer problem can actually spread, but it's not the only problem that you see, because we can see a lot of discards as a result of a group of nodes going down. So big MPI job crashes. We have problems with the fabric for a while because of that. So we may throw away discards, and they may be intentional ones, but you may be victimized as part of that too. And so this is weight data. This is the number of seconds that you're waiting on the system for stuff to get from one side of the fabric to the other. And so they vary greatly between the fabrics. There's actually about 4 billion of these, so as a percentage of total time, it's not very high. And that's for IB1, so this is interesting. These are actually, these racks have nodes that have DDR ACAs, but they're on QDR switches, and so the wait times are dramatically less on one side, but on the other side, actually, it's a little bit more. So they get busier, they wait more. So anyway, packet loss is problematic. Receive errors. They are spread out in time, but they're physically localized. And so in a retry mechanism, if you send it again quickly, you're probably going to get through, right? But a discard error is different. It's spread out physically, but there's temporal locality, so they happen in time. So the fabric has gone bad, you're going to throw away packets for a while, but then you're not going to do that for a while. And so you're going to wait. The best way to get the next packet through is to wait a while, because the network's messed up. And so you're not likely to get through, so you want to hold on to that. So the conclusion of this is that the nature of packet loss is bimodal. And so the retransmit mechanism actually does not deal well with both scenarios. And so where to fix it? And so this is, so of course I'm the little blonde guy there saying both. And so we're going to be beaten. So let's compromise. So, we'll try to fix the ULPs, but the truth is we have 5 different MPIs and 5 different versions of those MPIs installed on the system. We can't fix them all. And so where we can, I think we should try in software to make reliable connected mode more reliable. So not software, so that's in hard. So we'll try to fix the ULP, but we want to make the reliable connected mode more reliable. And so I think the proposal here is for IBTA, I'm going to take this back to them, is we want a logarithmic back off timer on HCA retransmit. And of course, we'd like to have more than 7 tries. And so this is the fundamental underlying issue, is that a reliable connected Q pair falls apart after 7 retries or 7 tries. And so you can set a timeout and you're going to fixed interval retry on that Q pair, and then when it's gone, it's gone. And so there are some cases where it's easy for the ULP to deal with reestablishment of that Q pair. Luster doesn't do it today, and there's a lot of really sophisticated software, so maybe they can fix that issue, but that some messages, ULPs make an assumption that maybe it comes from a very low level source, that I need to send this packet and it better get through because I don't have enough state down here to know much about what's going on. And so it'll get through. I very rarely do it, but on a big supercomputer, you're doing that kind of stuff all the time. And so that ends up bubbling up to the applications. And so that's why I think we really want in the HCA this sort of logarithmic back-off timer on resend, so that we send the first few packets quickly. That'll improve MPI performance. And then we'll wait a long time for the subsequent packets. And maybe we can't change more than 7 tries, but we want to get to the order of a minute or 2 minutes before we drop the connection. And so that's an important thing, and that'll fix a lot of software. And so that's it. of the IB crew and OFED community done a pretty good job. There's a lot of complicated software notes. There's some improvements probably we made, but that's it.